So we have one more general chemistry review module here. This is again an optional review module which will cover the basics of dimensional analysis to solve chemistry problems. And this is an optional review module in the sense that if you feel that you're good, you remember how to use dimensional analysis reflexively to solve chemistry problems. If it hasn't been that too long since general chemistry, you can gloss over this one, and as long as you're not struggling with dimensional analysis on the homework, you don't necessarily need to come back and check this out. But if you do need to brush up on how to use conversion factors in dimensional analysis to solve problems, or if you are struggling routinely with dimensional analysis applications on the homework, I'd recommend you come back and look at the problem we solve here to remind yourself of the basics. Obviously, dimensional analysis is a skill that we're going to use again and again and again throughout the course of this term. And in our next module, where we talk about how to convert between equivalent concentration units, we're going to use it extensively. So this is a very important skill, and if you're rusty at all with dimensional analysis, I would absolutely recommend that you come and give this module a thorough look and help you brush back up on the skill. Try the practice problems afterwards to make sure that you're using it effectively. But again, if you feel like you're still good on dimensional analysis, you can proceed past this video and move on to where we start talking about concentrations, which will be the main thrust of today's lecture material. Okay, so unit conversion and dimensional analysis are two equivalent terms, and they're both terms which are used to describe a general mathematical process in science of using a ratio between two equivalent measurements as a conversion factor to convert a measurement from one set of units to an equivalent measurement in another set of units. And obviously in chemistry, where we often deal with properties of matter that we can measure, and we need to connect those properties to something that is not so easily measured, like a number of atoms or a number of molecules in the sample when we're talking about concentration, dimensional analysis is used extensively to make these types of connections from properties we can measure to an aspect of the sample like number of molecules that would be much more time-consuming to measure every time we wanted to do an experiment. So in chemistry, we rely a lot on dimensional analysis in the sense that we build true relationships between established and proven connections between things like number of atoms in a specific mass of a sample or number of moles in a specific mass of a sample to solve problems, so that we don't have to redo measurements that people have done extensively and thoroughly hundreds of years in the past again and again and again when we solve problems. So the thinking behind unit conversion or dimensional analysis is that we can use these equivalent mathematical quantities that we call conversion factors to convert a measurement in one set of units to an equivalent measurement in another set of units that will be more useful for solving the problem that we're trying to address. This is something that you've probably done reflexively ever since back in kind of middle school or early high school. And it can be something as simple as knowing the relationship between number of centimeters in an inch to convert a measurement from inches to centimeters or miles to kilometers. But of course, in chemistry, we usually use it to connect something that's easily measured, like the mass of a sample, to the number of molecules in that sample through Avogadro's number and the definition of molar mass. The mathematical process behind dimensional analysis is deceptively simple. You take your original quantity and then you multiply it by a ratio called a conversion factor. And the conversion factor is a ratio between two measurements which expresses the mathematical relationship between any two types of units, such as inches and centimeters, as a ratio. And the idea behind multiplying the original quantity times your conversion factor to get a new equivalent quantity is that the conversion factor will allow you to cancel out the original units that your quantity was measured in and replace them with new units that are more useful for the problem you're going to solve. And as a result, you get an equivalent quantity. This is something that's probably ringing a bell, so I'm not going to go into a lot of specific examples. Instead, I'm going to go right into solving a basic scientific measurement problem with dimensional analysis and kind of explain the process as we go through it so you can see that example. All right, so this is a sample problem from section 1.1 in Harris, and we're told that a 100-pound human walking at 2 miles per hour burns 91 calories per hour. We want to know how much energy does this person use in kilojoules per hour. And we're given a little bit of conversion factor information in the sense that we're told that 1 calorie, little c, that's going to be important, is equal to 4.184 joules, capital J, an equivalent but different SI system measurement of energy. All right, so a couple of things to notice about this problem. Notice that when you're given a rate type of measurement, like a human walks at 2 miles per hour, we can express this as a fraction where we could say 2 miles, the distance traveled, goes in the numerator of the measurement, and the time it took, 1 hour, goes in the denominator of the measurement. Same for the human burns 91 kcals per hour. All right, so to solve this problem, we need to take this information given here, and our general strategy is going to be we're going to start with these measurements right here, a walking rate or a speed of 2 miles per hour, and a calorie burning rate of 91 kilocalories per hour. And then we're going to use conversion factors to figure out how many kilojoules the person would burn in a single hour of walking. Now, the challenge behind dimensional analysis problems is often that there's not one path or a set series of steps that you take, and if you always take the same set series of steps, you'll get the right answer every time. Instead, when you're solving dimensional analysis problems, you have to use conversion factors strategically to convert one aspect of your original measurement into an equivalent measurement. And you have to chart yourself a path from your starting measurement to the measurement that you want to end with, and how you use the conversion factors in between is up to you, as long as you're expressing correct measurement ratios with your conversion factors, and you're using them with the right orientation of the fraction so that the original units cancel out and you're left with the new units, you can solve any dimensional analysis problem, no matter how complicated. This one's actually surprisingly wordy, considering that it's only a 2-line question, but is still going to be basically solved in a single step. To solve it, though, the first thing we need to take note of is the relationship between calories and joules, because that's going to be our fundamental problem that we have to solve. Is we know that the rate at which our walking human burns calories in kilocalories per hour. So that's energy in the numerator of that measurement, time in the denominator of that measurement. We want the same measurement, essentially, in kilojoules per hour, which is an equivalent measurement of energy, but it's an SI unit of measurement. But it's an SI energy measurement unit. To do this, we're going to build a conversion factor. And the information we need to build our conversion factor is we take kilojoules and relate them to kilocalories. So it's worth pointing out that we're given all the information we need to do that right here. 1 calorie is equal to 4.184 joules. But to effectively construct our conversion factor, we have to remember a couple of things. First and foremost, the prefix kilo in the SI system indicates 1,000 times the original measurement unit. So if you're talking kilojoules, 1 kilojoule is 1,000 joules. And 1 kilocalorie is 1,000 calories. Here we run into a little bit of kind of a language issue, where in science, when you measure the energy unit calorie and it has a little c, that's not the same as the calorie you see represented on, say, the nutritional information packet label on a granola bar. Instead, when you see food energy measured in calories, that's calories in a capital C, or what we call a kilocalorie. So when we say that our human burns 91 kilocalories per hour walking at that rate, that's what we would typically in ordinary language call a calorie, this kilocalorie. So 91 capital C calories, a food calorie, is actually equal to 91 kcals, or little c calorie, 91,000 little c calories. And so notice our human's original walking rate is expressed in kilocalories per hour. We want to convert those kilocalories to kilojoules. That's not too hard. If 1 calorie is equal to 4.184 joules, there's going to be 1,000 calories in a kilocalorie, and there's going to be 1,000 joules in a kilojoule. So if there's 1 calorie, little c, or if there are 4.184 joules in 1 calorie, little c, then in 1 kilocalorie, there's going to be 4.184 kilojoules in 1 kilocalorie, or 4,184 joules in a kilocalorie. This is the key relationship we're going to use to solve the problem. This is where our conversion factor is going to come from. So to solve the problem, there are a lot of ways you can do this, but I'm going to do it really explicitly here because I want you to re-internalize the process and remember fundamentally how you use unit conversions to get from one measurement to another. Because when we do one much more complicated problems, it's helpful to be able to break it down to first principles. All right, so this is the conversion factor that we're going to construct. A conversion factor is a ratio, it's a fraction, where the measurement in the units, the definition of the units that you want your final measurement to be in is on one side of the fraction, and the definition of the measurements that you want to eliminate from your original measure, the definition of the units that you want to eliminate in your original measurement is on the bottom. So in this case, I'm just making the fraction 4.184 kilojoules on the top, 1 kilocalorie in the denominator. That comes from this relationship right here. That's how you build any conversion factor. And notice there's no right way up or down for this conversion factor. Which set of units I put in the numerator and which set of units I put in the denominator depends very much on the problem I'm trying to solve. But this is how I'm going to use that conversion factor. So my original measurement said that in 1 hour, my walking human burns 91 kcals. Notice it can be a little challenging to decide where to start in a unit conversion problem because there's lots of different measurements. We're told that our human weighs 100 pounds, that our human walks at a rate of 2 miles per hour, and there's a rate at which they burn calories. The question is, which of these do we start with? Well, because in this question, the focus is on how much energy does the person use, we don't need to know their mass, their weight, or their walking rate to know how much energy they burn because we've been told explicitly how fast they burn energy. So since I want to know how much energy the person uses in an hour, essentially, I'm just starting with their energy burning rate. They burn 91 kcals in an hour, and my only job then is to figure out how many kilojoules that is. To do that, all I have to do is one mathematical step where I take my original measurement and I multiply it by the ratio that is the conversion factor, and I line the conversion factor up in such a way that the definition of kilocals in the denominator will cancel the kcals in my original measurement here. The way that you visualize using unit conversion factors is to recognize that units cancel just like numbers. If I have kcals in the numerator here and I have kcals in the denominator here, the units cancel through division just like numbers do. And so my kcals will divide out. I'll be left with kilojoules because there's nothing to cancel the kilojoules, and I can find my answer by saying 91 times 4.184 kilojoules divided by 1 is 380 kilojoules burned in 1 hour. So I could express my answer this way. I could alternatively express my answer as, in scientific notation, 3.8 times 10 to the 2, and express it as a rate of kilojoules per hour. So hopefully, again, this was a useful review for you. If you don't remember much about dimensional analysis, I'm happy to talk more about this concept with you and run you through some more practice problems. If you feel like you're still pretty rusty on dimensional analysis and don't remember quite how to use it, I've included some optional review problems to follow this lecture, including a key that shows you my whole process for doing the dimensional analysis to arrive at the answer. But if for any reason you're rusty on dimensional analysis, please make some time to talk with me about it over Zoom or in person the next time we're in class. Dimensional analysis is something we're going to dive right back into, and it's going to be very fundamental to our lecture where we show you how to convert between equivalent concentration measurements. So don't neglect some practice on dimensional analysis. There's also problems that encourage you to practice dimensional analysis on the homework. If you're at all rusty on this, please, please, please come back and ask me, because this is the #1 chemistry skill, and it won't take you too much practice to get fluent in it again. But if you delay that practice, it's going to cause you some unnecessary problems down the road in this class. So if you have any questions on dimensional analysis at all, please take the time to ask me, and I'll see you in the next module.